Perfect. So yeah, my name is Iain Mackie, and I'm from the University of Glasgow, and I'm here to talk about query-specific knowledge graphs for complex financial topics. So a little bit of background about myself. So I've sort of oscillated between technology and finance. I originally did an economics degree at St Andrews. I then worked in quant trading for a number of years just over there, specializing in FX algorithms to buy spot and forwards. Moved back to Edinburgh, did a data science degree, worked in equity research, currently doing information retrieval PhD sponsored by Bloomberg, focusing on the kind of intersection of IR and knowledge graphs, while also doing kind of venture capital on the side, and we actually won the Alexa Challenge this summer. And I guess from all my experiences, whether it's trading, investment, or VC, fundamentally within finance, one of the most important things is answering complex questions. And generally the method for doing this, no matter what you are looking to do, is you search for relevant information and you reason a knowledge-grounded answer. So let's look at an example. So a question such as, how has the push towards electric cars impacted the demand for raw materials? A researcher would look over heterogeneous text sources, so whether that be Wikipedia, news, or Twitter, and they would extract, I would call it this kind of fuzzy graph of knowledge. So this is, anyone that's done research manually, this is your notepad of sources and key entities and facts. And then you would synthesize this down into your long form answer, so in this case, a document. But now if we're looking to automate this task, why is it so hard? Well, firstly, if we look at the kind of state-of-the-art ranking models, they really struggle with this category of queries. So some of the work that I did in SIG-IR 2021 with Jeff Dalton and Andrew Yates, we really focused on the state-of-the-art models and understanding where they perform good and bad in different categories of queries. And they really struggle with things that are non-factoid, multifaceted, long answer type, and require multi-hop reasoning. These are a lot of the key questions in finance. And now if we look at that kind of synthesization point, the factual accuracy of text generation, we already know a lot of the kind of issues, and there's lots of work on this in terms of hallucination, attribution of the knowledge. But in this specific use case, it's also the scale of information. We could have hundreds of relevant documents, hundreds of relative entities, and also the quality is directly attributable to the retrieval performance. And on top of this, we don't actually have a data set. And what would we require from this data set? Well, firstly, we need a set of complex domain-specific questions, and we need high-quality judgments for each components of this process. So this is document relevance, entity relevance, and also a gold long-form answer. So this is what work we've been doing recently. So this is CODEC, the complex document entity collection that we presented in SIG-IR this year with my colleagues at Glasgow. So how did we do this? Well, firstly, to look at the complex questions. We sourced domain experts across history, politics, and finance. So within finance specifically, we got traders, we had investment bankers, we had accountants, and we went, hey-ho, let's develop some really hard questions. So we came up with this criteria, and it was open-ended essay questions, natural language queries. They had to have multiple points of view. They had to concern multiple entities and can't be answered by a single document, and they require deep domain knowledge. And we used our domain experts in the set of criteria through multiple iterations to create a set of really complex domain-specific questions. And now for the answers, we almost did the reverse. So we took our domain experts, we gave them the questions, and we want a really extensive, good golden answer. And this was generally in the form of kind of 2 to 3 paragraphs, having really the key facts, the key entities, and covering the major points of view in this topic. So now we have a set of complex queries. We have these narratives or golden answers. We actually needed to construct this graph of knowledge and attribute good quality information within this graph. So we wanted to do it in a free text environment, so we chose Wikipedia as the entity knowledge base, and we generated our own document corpus using our domain experts to identify 25 high-quality sources of information. And then we employed annotators for 300 hours. It was a lot of annotation to interact with a search system and explore the topic extensively. What we found was if we just gave them the query, you get a very narrow pool of documents and entities. So what we did was we were like, go wild, explore the topic, reformulate it, not just electric cars, electric vehicles, go in and explore China's impact in the US, and dig down into whether it's lithium, nickel, or cobalt, and really allow them to explore this topic and ultimately provide relevance judgments to both documents and entities. It's about, 17,500 overall, scoring them between 0, so not on topic, 1 being on topic but not useful. If you imagine that almost be a kind of footnote to your essay. 2 being it's relatively important, it's an entity or fact that might be in, let's say, the meat of the article. And 3, absolutely critical, you need to understand this. And now to kind of flip back, so why do we care about retrieval in this setting? And I think the first thing is, when you're looking at something like finance, you need to have the information there. Anyone that's looked at an investment or written a report, missing information, not having a clear picture is super important. So you really need high recall. But on the flip side, we also need strong precision. We don't want to have errorless information in your graph of knowledge. For example, cobalt network should not be in this graph. So what we did was we took the CODEC data set and we looked at the kind of current ranking effectiveness of state-of-the-art search systems. So that's sparse systems, dense retrieval systems, neural re-ranking systems. And what you can see, I won't go into too much detail here, but these are a lot harder than a lot of the current retrieval data sets. So Trek Deep Learning, that's based on MS Markov queries, are generally some of these kind of factoid, almost QA-based stuff. So this is a lot harder, which creates certainly challenges. And then what was interesting even more so was when we look at the individual subsets of questions, finance is actually by far the hardest. And that's for both document and entity ranking. So that's about 10 to 15% lower in both kind of recall metrics and precision metrics. And digging into some of these failures, what was clear was that these kind of current retrieval models couldn't really do some of the complexities that you need within the finance domain. For example, filtering on events and specific entities or categories of entities, specific reasoning of, over latent knowledge. Perhaps that's multi-hop across multiple documents. And there was also this interesting aspect that a lot of these systems were good with, let's say, the head named entities, but these sort of like latent concepts that's really important in finance, whether that be a cyber attack or transaction cost when you're talking about Bitcoin, they didn't seem to capture these. So now that we have, the CODEC data set and we've got aligned document entity judgments, we then thought, well, what happens if we connect both tasks? And the obvious way to do this is through entity linking the document corpus. So then this can give us our, in essence, free text knowledge graph. So we wanted to understand how these two tasks were related. So what we did was we calculated the percentage of categorized entities within each document, and we pivoted that against the actual document relevance. And as you can see, the documents with the highest proportion of very valuable entities in them are statistically more likely to be relevant, whereas the reverse can be for those that are not relevant. And we took this a step further and we're like, hey, well, let's actually incorporate entities directly into the document ranking. So what we did was we took the original query and we, appended entity feedback, so demand, cobalt, electric cars, and perhaps unsurprisingly, the effectiveness, even with a kind of simple baseline method, BM25, increases substantially. But what we really wanted to do was to address some of these fundamental issues that we saw with the retrieval models, and we actually want to cast this in a knowledge graph construction context. But always the hard thing is how do you actually evaluate this? So the cool thing about CODEC and having these aligned document entity judgments is we can actually define something that we call a golden graph. So this is where we basically take the set of relevant documents as kind of like the golden nodes, and then we also say the entities that are relevant and mentioned within these documents as also in this golden graph, and we assume that all edges that are connected, those two nodes, are again part of that golden graph. And I think the key here is that these graphs are very large, and I think we're having a chat with some people about QA graphs in the coffee break, where there's effectively one relevant node. Unlike the difference here is you see there's 44 documents, there's 25 entities in this formulation, and there's thousands of connections between the documents and entities. So they're, very large. And now what we wanted to do was use our strong baseline retrieval systems and actually have a go at constructing some of these graphs. So we took BM25 plus RM3 plus T5 for the document ranking system, and we're able to basically vary the level of K documents, so basically the number of documents between rank 1 and rank K that we would add to our graph. We took the entity ranking system, BM25 plus RM3. The K ent in this case basically acts as a filter. So because it's a topic-specific graph, you don't want all entities in your graph that's mentioned in the document, you only want the entities that are relevant. So we effectively take our full documents, we then filter all the entities that are mentioned in them based on relevance and construct our graphs. What's cool here is now we can actually look at the precision recall trade-offs as we vary those levels of K and increase our graph size. So you see if we kept both Ks at 10, so 10 documents and the 10 most relevant entities, you can see you get actually relatively high precision, but you miss most of the information. Whereas if you put K out to 1,000, you can see you actually do manage to capture a lot of the information, but they're incredibly sparse graphs. And what this certainly makes clear to me is the fact that there is these huge trade-offs between precision and recall, and that there's firstly also lots of headroom to improvement. But the fact that we can benchmark this means that for downstream tasks, you can actually then optimize it. And then I guess just to conclude, so firstly, current neural ranking systems certainly do struggle with these kind of complex financial research topics. I think we've certainly tried to motivate that using a free text topic-specific knowledge graph can support many domain-specific tasks. In this case, we're focusing on kind of long-form answer generation. And that CODEC, is a pretty useful resource. Hopefully, some people can use it in this room, and it's able to allow you to evaluate specific components of that so that you can optimize it based on a component level. And just at a high level, some of the things that I'm sort of using this for and looking to extend into. So I'm really interested in kind of adapted knowledge-based retrieval. So it's like we looked at a very static level. We took two retrieval runs, and we were like, hey, let's build a graph. Actually, it's iteratively searching the index to add more information based on the graph state. There's been some interesting work in QA about using kind of graph models to leverage both the structure and kind of LLM embeddings. This is a slightly different problem in terms of the kind of size of these, but I think trying to use some of these would certainly be an interesting aspect. And I think as we saw, these complex topics can't just be represented as a single query. So for multiple, trying to break that into multiple queries or facets and use that to optimize kind of our graph construction. And some of the challenges, as I mentioned, this sheer size of some of these graphs that create, huge amount of sparsity, and getting kind of high quality training data for this. Obviously, this is more of, I would say, a test set based on the size. We also need to actually get some, deeper judgment. So I think that the next thing we're looking to do with this is we have the relevant entities, we have the relevant documents, we have the long form answer. But in this case, we actually assumed that all the connections were relevant between the two. Obviously, in reality, that's not the case. So the next phase will be extracting those facts and be able to basically drill down a bit more exactly which ones are the key. Thanks a lot.
Questions?
Thanks for the very interesting talk. My question is really open-ended, and so I actually maybe related to working with some people in the room, is that there's obviously there's a problem with a lot of information, but also problem with potentially inconsistency across different type of information, and some of that you could have Wikipedia say one thing and analysts say another, and that is not so much. Some of it is fact verification, some of it is whose opinion against who. So when you have such issues in financial data, how do you deal with it?
Okay. Yeah. I guess firstly we've tried to hopefully push this into the data set. We're looking for things that actually are controversial, have debate. So really, I think here it is you want to have access to that information. I think it'd more be a downstream system to try and work out if that, X is right versus Y. I don't think that's something that we focus on specifically. We construct it to use high quality sources. So that's kind of the way we've, let's say, sidestepped it. But yeah, certainly in the wild, this is really important and a big challenge.
Thanks, very interesting talk. Can I just go back to the point about why finance is harder? I may have missed something, or this may be a reframing of what you said, or it may be a different thing.
Yeah.
But are there sort of structural answers about the graphs as to why it's harder?
So I will be looking at this next week. Is my honest answer. So on this GitHub, there's actually a paper that I did for this thing that I still need to look a bit more detail. My initial thoughts are, particularly compared to history, where events and people are very named entity. This happened in this event, and there isn't much debate. Finance is very fuzzy. I also think the question categories are very different in terms of what you're looking from an answer in finance can be a lot more fuzzy rather than I would say in history. There's normally two very specific sides of the argument, I would say. But I'm going to post something on archive addressing this exactly.